Okay, everybody, welcome back to the Intellectuary channel. Today I will be providing an introductory lecture to differential equations. So what they are, how can they be used in calculus, and a few examples of how we can solve them. So first, let me introduce this concept of a differential equation by defining it. So the definition, I would say, of Formula 1 would be that a differential equation is an equation that relates any quantity. So when I'm talking about any quantity, this can mean like water, pressure, temperature of something, and like even population growth with respect to its derivative. So this means rate, right? Derivative we can assume as rate over time. So this is a formal definition. It's an equation that relates any quantity with respect to its derivative over time. Now that we've learned its formal definition, we can now look at the structure, right? We have different types of differential equations, right? Separable, non-separable. We're going to work on the separable differential equations type here in this video. So this is going to be its structure for a separable differential equation, right? Calculus 1. So it's going to be d on the top, right? On the numerator, d something, right? This is a quantity. So d plus a variable that represents a quantity on the numerator on the top over dt. And most of the times it's dt because, we have over time. Now, over time corresponds to this, right? Respect to time. So over time, that part goes here. So now that we have, d some quantity over dt is equal to an equation, or is equal to something. Now, this something can usually be of multiple variables. This something can also be of a single variable, right? We don't know. There's a lot of different types of separable differential equations that, there's so much variety we can't really define anything here. So now let's look at an example, right? And this is a really common one that a lot of Calculus 1 students will learn in class is the one for population growth, right? dp dt is equal to. So here, what we have here is a differential equation, right? So a differential equation that relates to population growth. So this is an example of how something is really applicable to us, and something that we can use, right, in our daily life. It's not just a math concept that's abstract. So we look at this here. Let's rewrite it again. dp dt is equal to kp. Now, realize we have two things here, right? Two components. We don't know if the k is a variable or a k is a constant. But in this case, let's approach k as a constant. Okay, so p is the only variable here. So we have d quantity, so d population, right? That's the quantity over dt is equal to kp, where k is the constant, and p is the variable. Okay, so now that we've got that down, we can actually try to understand what the first step to solving any separable differential equation is. First step, separate your variables, right? Separate your variables. When I mean separate your variables, for example, any equation you have x plus 1 is equal to 2x, right? What you have to do, this is just an example, by the way, not a differential equation, but a regular equation. What should you do to find the value of x? You get all the x's to one side, right? So minus x, 1 is equal to x, right? So x is equal to 1, right? How are we supposed to find the value of x? because we isolated the variables on one side. So isolated x on the other side, isolated the constants on one side. Now here it's basically the same thing, except we're dealing with a differential equation, right? So separate your variables basically means isolate your variables on one side and your constants on the other. Here we have k as a constant and p as a variable. So the first step would be d. So let's rewrite it, right? Make sure we got everything here that we need. Okay, so how would we separate it? Well, first property of separation of variables here, in a differential equation, any differential equation, the dp or the dt cannot, and I am stressing on this, cannot be in the denominator. This absolutely cannot happen, otherwise you're going to get an incorrect answer, or you're not going to get any answer at all that makes sense. So when you're separating this, well, you can go, okay, nothing crazy is going on. You can just say dp is equal to, or you can say actually, sorry, not pdp, it's 1 over p, right? dp over p is equal to k dt. So how we separated the variables is, well, let's imagine this, right? Kp as a fraction of 1, right? Over 1. So what we do is we have to isolate p and dp on one side, right? So the left side. What do we have to do to get rid of this from k? We just have to do the reverse operation, right? It's getting multiplied by k, divide it, right? So 1 over p, that gets canceled out. 1 over p, right? So the p stays on the bottom, and you're ensuring that you're doing the right math, right? The dp stays at the top because it can't be in the denominator. So where does that go? Well, then that goes dp over p is equal to, okay, now we have this dt. Well, we know that we can't have a dt in the denominator. So what do we have to do? The reverse operation, right? You have to multiply by the reciprocal. So the reciprocal is basically, or the opposite is basically dt over 1. This cancels out, and you get k times dt over 1, which is basically dp over p is equal to k dt. Okay, so that's how we do the separation of variables step. Now what we have to do is we have to integrate. So step 2, integrate, right? This is the really important part. And this is where the actual calculus comes in, I feel like. Because this was all just rearranging algebraic skills. So we integrate, and this is just a integral like that. And so when you integrate, right, you have ln, or natural log of absolute value of p, is equal to kt plus c. And obviously you have to have a plus c whenever you're evaluating an indefinite integral. But in this case, if we do that, and because we know c is just a constant here, if we do that, then the c's just cancel out. And we need to have the c, right? We need to have a plus c at least on one side so that they don't cancel out. Only on one side though. So I did it on the right side. You can do it on the left side if you want. So we have that. ln absolute value p is equal to kt plus c. Now what we have to do is exponentiate. And so what I mean by this is you have this right here. Well, all you have to do is, exponentiate. So you put everything to the power of e, right? It goes e to the power of everything. So e to the power of ln p, absolute value p, is equal to e to the kt plus c. So you have an e here, you have an e there. So we basically exponentiated. Now, e to the ln of x just cancels out, okay? So if we have e to the ln of p, the e to the ln cancels out, and p is, well, we don't know if it's negative or positive, so it's just going to be positive for now. So it's just going to be p, right, is equal to e I know, yeah, e to the kt plus c. And here, what p actually is p of t, right? Because this is a population function, right? If we go back to what our original thing was, right? This was for population growth, right? Population growth differential equation. So this is a population function. So obviously we have to have p of t, right? Because if we plug in any time t, we should be able to get the population at that time t. So then we have e to the kt plus c. Now, what we have here is we have to remember our exponent rules, right? P of t is equal to e to the kt times e to the c. Now, right, because when exponents are added, you can separate them like this, right? That's the same thing as that. Now, let's let e to the c equal a, right? Equal a constant a. So with this, right, we have p of t is equal to a to the e kt, right? And so that gets figured out really fast, right? Because it's the same thing. We just substitute this for a, right? And we just get a over here. So we have our population growth function as p of t is equal to ae to the kt. And so a is basically going to be our initial population at time 0, right? So if we have, at time 0, population is, let's say, 10 people. Well, we have a point that we can get, and so this actually is this equation we have here is called our general solution. It's not an exact answer, right? We don't have all the parts to the equation that we need. We don't have the a, right? So we can't, or the k, so we can't really, we don't know what to do with that yet. So it's just a general solution. The next thing we can do with this information right here, is we can create a point. Times 0, 0, comma, 10. Right, so this is t, and this is p of t. All right. So what we can do with this is, well, we can substitute, right? So when they say p of 0 is equal to 10, right? We can say, okay, 10 is equal to ae to the kt, which is 0. 10 is equal to a e to the k times 0 is 0. So 10 is equal to e to the 0 is just going to be 1. So it's just going to be a times 1, or a is equal to 10. So now this is our actual initial condition. So this information that they give us, right, in any situation is called an initial condition. It's usually most commonly found to be a point, right, or at something times 0, something is this amount, so that when you plug it in to this general solution, you'll be able to find something known as the particular solution. And a particular solution is basically something where you have all the parts to the, differential equation solution. So compared to our general solution where we don't have an a, we actually have an a here. So we have p of t, right, its population growth is equal to 10 e to the kt. So with any time t, we would be able to find out, okay, what is the population, right? Or we could even find out the k if we wanted to, really, with a calculator. So this is just going to be something called our particular solution, right? So we have two things, or actually three things. We have, first comes our general solution, right? So after you solve a differential equation, any separable differential equation, you'll have a general solution, right? It's usually, y, or any function is equal to ae to the kt, right? So that's the general structure for a general solution. 2, you have your initial condition. If it isn't given to you, then you just find your general solution and that's it, right? You're done. But when you're given an initial condition, then that's different, because then they gave you information about when time is equal to 0, right? So 0 comma something, right? And so you plug that in to the general solution to find, the product of that is the particular solution, where you have a is equal to something, and you have a defined function. We have, y is equal to something e to the kt. And that's something you already know what it is, so it's known. It's a known quantity or a known numerical value. So that's all I'll discuss within this lecture of introduction to what a differential equation is. And if you guys have any comments or questions, please do put them in the comment section. Don't forget to like, share, and subscribe to not miss out on any updates when I post any kind of calculus or other math videos or any STEM related videos with science as well. Yeah, thank you.